Hello everyone, it's Mr. N here again, and today we're going to go over some of these cross-sectional area additional problems. This is a worksheet that you guys got, so I'm going to go through and make this video on it. In the first question it says, a solid has a base that is a circle, x squared plus y squared equals 9, and all cross-sections parallel to the y-axis are squares. Find the volume of this solid. Okay, so let's go ahead and draw out and graph what we have here. So we've got this situation where the solid has a base. A solid has as its base is this square. So this is an equation, a circle. This is an equation of a circle with radius 3 right here. So we're going to go out 1, 2, 3, 1, 2, 3, 1, 2, 3. So it looks like this. This is the base of my solid, this circular pattern here. And what we've got going on is that the cross sections parallel to the y-axis. So parallel to the y-axis, these cross sections are squares. In other words, I have squares coming out of the paper like this, parallel to the y-axis. So these coming out right there are squares. So three-dimensionally, this will have a circular base, and then you've got these squares that just come out of it like that, kind of coming out of the paper. So looking at it in like a three-dimensional sense. So we have to find the volume of the solid. So the volume in this case will be the integral of the area dx. So even if we're dealing with cross sections here. Now, the cross sections are squares. So I'm looking for the area of a square. So if I draw out a square here, this is x by x, the area will be x squared. So that's what I want to integrate. But now, what is the length of this x? Well, it's going to be what? Right here, the length from the top to the bottom of the circle. The top of the circle is, over here, if we solve for the y value, is going to be y equals the square root plus or minus 9 minus x squared. So the top, from here down to the bottom, the top is going to be the square root of 9 minus x squared. The bottom will be negative root 9 minus x squared. So that's the distance that I'm going in each one of these squares. So that's the length of that base. So that's what I'm going to use in my volume equation. So we have the volume equals the integral. Now we're going to go from negative 3 to 3, okay, because that's the slices right here to the x. So we've got negative 3 to 3 of, now this length will be from here to here, so it'll be 2 times 9 minus x squared. So this length is 2 times 9 minus x squared. That's what each x is, squared dx. So that's the length from the top to the bottom. Okay, so we're going to go ahead and integrate this. And we get the volume equals the integral from negative 3 to 3 of 4 times 9 minus x squared, after I square that, which ends up being 4 times the integral from negative 3 to 3 of 9 minus x squared dx. Forgot the dx here, which ends up being 4, and this will be 9x minus 1/3 x cubed after I integrate this on the bounds from negative 3 to 3. And this answer ends up coming out to be 144 cubic units. Okay, moving on to number 2. And in number 2, it says the base of a solid region bounded by the parabola x squared equals 8y and the line y equals 4. And each plane, that should say plane section, perpendicular to the y-axis is an equilateral triangle. Find the volume of the solid. So let's take a look at what we've got here. We've got this situation with this graph this time. And in this graph, we've got this parabola. 1/8 x squared is y, which is the parabola we're talking about. So that's going to end up looking like this. And this will be right here, the line y equals 4. So when y is 4, 1/8 x squared equals 4. So when y is 4, I'm going to get x as being plus or minus the square root of 32. So this is at root 32 here. This is at negative root 32. And I've got this coming up at 4 right there. That looks like that. And the slices this time are perpendicular to the y-axis. So I'm slicing this in this manner, perpendicular to the y-axis, and these slices that come out are equilateral triangles. So these are equilateral triangles coming out of the paper three-dimensionally at you. So if I take a look at an equilateral triangle, and I want the area of this equilateral triangle, we developed this in class. Remember, the area is 1/2 times the base times the height. Since it's equilateral in this case, actually, I'm sorry, we developed the we did develop the equilateral in class. So let's go ahead and do it again anyway. So since this is equilateral, this is my base B, this is a side length B as well. So this piece right here will be B over 2. This will be a 60-degree angle. So that means the height is B over 2 times the square root of 3, using the principle from 60, 30, 90 triangles. We know the volume is going to be the integral of the area. And in this case, I'm going to need dy's because I'm slicing it in this manner, up along the y, from 0 all the way up to 4. So we've got to find what that area would be. That area would be, right here was what we're looking at, 1/2 times the base, and then the height we said is B over 2 root 3. So I end up with 1/4, or we'll say square root 3 over 4 B squared. So now I need to find what the length of that base would be. So the length of this base would be, if I took a section from here to here, is what I'm looking at. We would go back to our formula here, and I need this in terms of y, so I'm looking right there. So I need from this x value to that x value. So at this x value, I'll get negative root 8y. At this one, I will get 8 root y. So the full length, again, this would be halfway at the origin right there. The full length would be this negative 8 root y plus the 8 root y. So this whole length would be 2 times 8 root y. I'm sorry, 2 times the root of 8y. Sorry, I've said it backwards again. Okay, so the area ends up being root 3 over 4 times this 2 times the square root of 8y squared. And cleaning this up, we will end up with, the 4 goes there, it goes away, 8y, so 8y root 3 as my area. So the volume is going to be from the integral from 0 to 4, from here all the way up to there. That's the way I'm taking my slices. And we said these equilateral triangles will have an area of 8y root 3. That's what each of the areas will be, dy. Again, dy, because I'm taking my slices up along the y, all the way up to the top. So we go ahead and we can integrate this and find the work in between, and you'll end up with 110.85 cubic units. You can go ahead and use your calculator on this one as well. Remember, the 8 and the root 3, these will be constants, so you could take that out in your integration from 0 to 4, and then just integrate y, dy. And that's the answer you should get. Okay, moving on to number 3. Let's take a look at what we got here. And number 3, the base of a solid is a region enclosed by the triangle whose vertices are 0, 0, 4, 0, and 0, 2. So the cross sections are semicircles perpendicular to the x-axis. So let's go ahead and draw this out again. It's enclosed at 0, 0. And then over here, well, my axis didn't look so good. Over here is going to be 4, 0. And then up here is going to be at 0, 2. So this will be 0, 2. So I'm looking at a shape that is this triangle right in there. And the cross sections, so I have this triangle, and the cross sections perpendicular to the x-axis. So now I'm going to take these cross sections in this manner, perpendicular right here to the x-axis. So I'll end up with a dx, and I'm going to integrate from here to here, since I'm slicing it this way. These are semicircles, so I've got little semicircles coming out of my paper at me like that. Okay, so what are we integrating? We're integrating a semicircle. So the volume is equal to the integral of the area, and in this case where we said we're going to slice some dx's all along the x, and we have semicircles. So we need the area of a semicircle, and in this case it's 1/2 pi r squared. Well, what's the radius? The radius is going to be from here to there, right? So we could take this whole diameter and cut it in half. So the radius, remember, I need to now come up with the equation of this line to be able to find my y value, because I wasn't given an equation this time. Well, over here we've got y equals mx plus b. B is at 2, and we can quickly find the slope. We're going to go down 2 over 4, so that's going to be -1/2. So y equals -1/2 x plus 2. That is the equation of this line that bounds that region. So now I can use that to help me find my radius in here. So the area, we said, is 1/2 pi r squared. And in this case, it'll end up being 1/2 pi. And the radius is going to be this equation. We want half the distance from here to here. Again, from here to here, we want half that distance. So there's the 1/2, and here's that distance. That distance is going to be -1/2 x plus 2. It's the equation of my line squared. So cleaning all this up, I end up with an area being pi over 8 times -1/2 x plus 2 squared. All I did was just clean it up a little bit. You can leave it in the squared form. So our volume is the integral of the area, which will be this time along the x's, so from 0 to 4 of ax dx. So this becomes 0 to 4, and I've got pi over 8 times -1/2 x plus 2, this quantity squared, dx. We can go ahead and work this out. We get pi over 8, and when I integrate this, I'll end up with 1/3 times -1/2 x plus 2 to the third times my -2, because that's the chain rule part that I need to take into account on the bounds from 0 to 4. You might want to use U substitution there if that'll help you out. And then over here we end up with negative pi over 12, -1/2 x plus 2 cubed on the bounds from 0 to 4. This comes out to be 0 minus -8 pi over 12, which gives me a final answer of 8 pi over 12. So this becomes 2 pi over 3 cubic units. Alright, hopefully that helped you get the idea of how we find cross volumes using cross-sectional areas of known cross-sectional areas. And in this case we had a few examples here. This was a semicircle in this example. This one, the cross sections were equilateral triangles, and in this one the cross sections were squares that came out at you. So hopefully that helps, and good luck.